All right, good afternoon. I owe you guys some apologies about the homework, as maybe usual. I'm going to get there in a moment. Um, so if you haven't passed up your homework, please do so. In the assignment itself, I told you there was going to be Excel required on a couple problems, just to kind of give you a heads up. I intended to give you a little better preparation for that, and then I unfortunately did not. And this week I had some trouble with that example, trying to reproduce it in Excel myself. So I told you guys I was going to try to Tuesday, and then I told one or two of you yesterday that I was going to try to, and I spent some hours on that, and still wasn't able to reproduce what the solution are. So I can show you a little bit of that. The other thing I need to apologize about. So sorry I didn't get that to you, that Excel file like I wanted to. I just wasn't comfortable that I had it in the right shape. The other thing was 10.9 was probably the better one to need Excel, not 10.7, because I think I said don't do 10.7b or C or something. And so 10.7c maybe it was needed, but 10.7 generally probably wasn't so necessary. So anyway, I apologize for that. I've made some harsh critiques for myself for next time I teach the course to get that in better shape for the next batch of students. Anyway, one step at a time. Speaking of harsh critiques, please feel free to use the online course evaluation. You are welcome to be harsh. You're welcome to also let me know what you did enjoy or whatever you see fit. So my apologies. What I'm going to do about it is be very lenient on 10, 3, 7, and 9. Okay? So if you made an effort, that's what I care about. And you'll probably get full credit if it was clear that you made an effort. You'll see well, I'll go through as much of it as I can, and maybe I'll even start a little bit with the example 1014 to kind of show you what I was doing. Hopefully I can provide you enough information and enough insight to see the approach, and I'm wanting for us to learn from it. And I think we can do that today and through the homework assignment. I will also say that I do not want to give you a take-home exam where I would try to make you do some Excel, because I just don't feel like I covered that appropriately. And so I'm planning to give you in person with a little bit simpler of a task. Okay? So I don't know if you like that or hate that. See some sad faces don't like it. So you want some Excel work for take home? You would much rather. Okay, so what about the take home exam is that you like? Is it just that you know you'll do better?
We can spend as much time as we want.
It's the time. You want to waste a lot of time on this, not doing research? Trying to study and okay.
I would prefer the ability to, like, if we had it available by Friday due on Monday, like being able to work on it earlier and kind of like get it out of the way earlier, but like also having enough time to work with each problem.
Okay. Any opposition to that? Next Friday. Got a comment? So that doesn't work so well for you, right? I mean, what would happen if I gave you from Monday to Tuesday? It's like a 24-hour period or something like that. Exam on Tuesday? Or perhaps like a 2-day period, Monday through Wednesday or something like that.
I like the idea of having it at least by like
Sunday through Wednesday or something, maybe. It doesn't hurt to try, right? No exam. Thanks. All right. I'll give that all some thought, and I'll email you with my decision tonight or tomorrow. Okay. And if it's going to be a take home, then it would be yeah, it would, I will post it either Sunday or Monday and give you, I guess if I'm posting it kind of during exams, it would be at least 48 hours. But I'm going to think on that, make my decision. For the moment, expect to be here Monday, I think at 3 p.m., right? So just plan on that. Don't make other plans, and I'll think on it. Okay, so all that said, I'm gonna cover what I can from the homework. We'll show you. Actually, you know what? I think I will go ahead and start and show you my approach to example 1014. So the problem, if you go to the book, there was something I noticed in the discussions kind of beyond the graph. It was a little unclear where the example finished, but at some point it made the statement that we can assume that hydroxyl radicals will each reach an equilibrium state in the production and consumption such that we have this equation here, that the rate of reaction that's forming the hydroxyl radicals, which would be the ozone with the HO2 minus, is equal to the rate of consumption of the reaction of hydroxyl radicals with the atrazine in that example. So that changes a few things, and I'm not sure if I quite got things in place to calculate that appropriately, but I did finally with that. I got the stage, the case one, where we were neglecting the hydroxyl radical concentration. I was able to plot that. Where did my plot go? My pad it plotted, and I don't know where it went. Oh, it just wasn't rendering. So I was able to get case one to plot appropriately eventually, and so I'll walk through that. The other ones were decaying too quickly, and I have some issue with the Excel file or with my assumptions that build into that. I'm not sure. So anyway, this rate would allow us to simplify the change in atrazine concentration according to this reaction, and that's what I was aiming to apply. At some point, I ran out of time, so I'm just going to show you the case one, what I did. I set the initial conditions according to what we knew the initial conditions were for the atrazine, the ozone, or for 0 for the reactive intermediates that are without anything happening should be at 0. From there, I calculated the different pieces. In one thing I did was I noticed that my HO2 minus concentration was going negative sometimes when I had the equation. Perhaps I wasn't taking small enough time steps, but when I took them smaller, still having some issues. So I used a function called max in Excel to set it. I think it can do a few things, but one thing it can do is to say at the minimum value this is going to be is this number. So I put the minimum set to 0. It's kind of a weird thing to say. It's the equation, the function is called max, but I think it would be a minimum for this number, and you could probably do comma max or something like that. This Excel syntax is just what it's going to do. So anyway, that was to make it so that it never dropped below 0, so that it would always return a mostly reasonable approximation. I think I might have some issue there still, but at any rate, the rate of change was more dictated by the reaction of atrazine with ozone. And so that's ultimately what was coming out of the equation. Ozone will change a little bit, and atrazine will change as well. So ozone is going to be changing according to the 3 different reactions that are consuming it. And I put each one of those in there with the, so I would take the rates listed here and essentially multiply the instantaneous rate calculated in each component times my time step. Okay, so I would take a delta t, which I set to 1 second, and so I'm doing 1 second time steps, and during that second, I'm calculating according to what the concentrations were at the prior second. Now, I think there are several different ways of doing this geometric integration, and perhaps maybe taking an average of this one and a guess of the next one or something like that might be a better way to do it. I was just taking the previous one and working from there. So there may be some refinement possible, but this should get us very close. So going from there, I did that with each setup. So the atrazine got the same treatment, essentially in case one without the hydroxyls. The HO2 minus had formation with ozone and the OH minus. And hydroxyls, not that they mattered here, but they were going to be forming once we had some HO2 minus. So that was my aim. That was my beginning place. And as we'll talk about as we go through the homework itself, I think 2, 3, and 4 might require a little more attention to the HO2 minus in terms of that's probably in equilibrium with hydrogen peroxide. So that might actually be primarily hydrogen peroxide, and I didn't notice and catch that, and there was no mention of that in the example solution. So that might be the missing part. A lot of that HO2 minus would go to hydrogen peroxide, and then we would have less here. Anyway, that was the general approach, and the point that I hope we'll see with the homework and with this is we can take a rate equation and in an instantaneous moment calculate the rate. And if we have a rate, a mass change per time, then we could apply a really small time step to understand how much change occurs, right? So normally we integrate, and we do that if we're doing a formal integration, we are not doing a numerical method. We derive some new equation based on time. But instead of doing that, we could do a numerical integration and give it some defined time step, time approach, the dt approaching a very small number. Then we can plot it and understand and use that accordingly. So that's the aim. And if nothing else, it is quite handy to be able to point out the initial rate at which things occur. And so some of the homework problems we will look at do exactly that. Okay. Did anybody do problem or make an Excel sheet like that for 1014? Just because you wanted to? I didn't think so. Just checking. Okay. It's not assigned. That was just an example problem I had pointed out to you on Tuesday, that you could look at it in reference of a couple of these problems. So that was just, ideally was a reference point. But all right, so let's start with a simpler problem. 10.2 is more just a mass balance type of a problem. We have a utility planning to treat a water supply containing 0.8 milligrams per liter of manganese 2+ by addition of chlorine dioxide. And that's going to precipitate manganese oxide solids, MnO2. If the reaction converts ClO2 to ClO2 minus, how much MnO2 solids would be produced and how much CO2 would be consumed in 1 day of operation if the plant was at a plant producing 40,000 cubic meters per day of water. Okay, so we have some parameters, and we're going to need a reaction overall. So if we take a look and consider Mn2 plus reacting with some amount of chlorine dioxide to give us manganese oxide solids and some amount of ClO2 minus. We need to balance that. That's going to be our redox chemistry. If we could split that into half reactions and do the balance. Ultimately, what we'll see is it would probably make sense to also have water here on the left because, let's see, and protons on the right. So let me give myself a little more space here. All right, and the way we will come about that is we will see to balance the oxygen on the left side, we have Mn2 plus and ClO2, and then manganese oxide on the right. So having Mn, not M2. Okay. What we will find if we do the redox balance, we actually need 2 chlorine dioxides to drive this reaction, which means we'll have 2 of these on the right as a product. And to match the charge then, we will end up needing, since we now have a -2 from the ClO2 minus and a +2 from the Mn2 plus over here, we need several protons. So if we add 4 here, 4 H plus, that's going to balance us to get both sides to a net 2 plus. That means we need 2 waters on the right to balance out those protons. And if we go through and check that, we have 2 oxygens in the waters, 4 oxygens in the 2 ClO2 here, 2 oxygens in the MnO2, and 4 oxygens here. So we're all balanced. So we need some balanced equation like that. And then we may also need some molecular weights to be calculated. So we can take a look at manganese oxide solids. The molecular weight for that should be 87 grams per mole. For chlorine dioxide, this is 67.5 grams per mole. And manganese is 55 grams per mole. Okay, then essentially we just need to set up a big balance to say 0.8 milligrams per liter, change that into moles per liter, apply our ratio between chlorine dioxide and manganese, a molar ratio, convert into chlorine dioxide that we need, convert a few units, and we will be good to go. So I'm going to do all of this in kind of one big line here. 0.8 milligrams per liter that we have in solution. We can multiply this by, I'm just going to call it 1 millimole of manganese per 55 milligrams of manganese. That's moles per gram, but I just went ahead and put it into milligrams and millimoles, and I'll do the same with 2 millimoles of ClO2 per 1 millimole of manganese. That's just coming from our stoichiometric balance up here. We needed 2 chlorine dioxides per 1 manganese that we're oxidizing. From there, we want to convert back into mass of chlorine dioxide, so we will take 67.5 grams per mole, going to say milligrams per millimole of chlorine dioxide, and then convert from I guess milligrams to kilograms. We can say it's 10 to the minus 6 kilograms for every milligram. And then we're going to do that because we've got a large amount of water to treat. This would be 4 times 10 to the 4th cubic meters per day, and also multiplied by our conversion from liters to cubic meters. So 10 to the 3rd liters per cubic meter. We do all of that, and our units should come out and give us kilograms per day of chlorine dioxide. This would be 78.5 kilograms per day of chlorine dioxide. Okay. Any issues there? Okay, pretty straightforward. We'll do the same thing to get the manganese oxide solids. I'm going to start with the same starting place. This time we're doing the 87 milligrams per millimole of the solids. And divide that, we'll just go ahead and do the conversion right here, divided by 55 milligrams per millimole of the manganese. Multiply that by our conversion for the liters, 10 to the third liters per cubic meter. And again, the flow rate. 40,000 cubic meters per day, and convert it into kilograms. That should give us a value of 50.6 kilograms per day of manganese oxide. Okay. All good with that? All right. So the fun begins. So 10.3a, I went ahead and gave you the book solution to this part to make sure you're getting kind of the crux of the problem before jumping into the more complicated pieces. It's also it's very much similar to what we just did on 10.2. So here we have a metal plating facility with a waste stream at pH 6.5. It contains 6 milligrams per liter of cyanide, expressed as Cn-. That is, and we are proposing to oxidize that to an innocuous cyanate ion, CnO-. I'll note that that is a completely different thing than Cn. So HCN and Cn are in equilibrium, has nothing to do with the CNO stuff. Okay, and that's which is reduced to chloride in the process, so the chlorine dioxide goes to chloride. So part A says, write a balanced redox reaction and determine the dose of chlorine dioxide required to leave a residual chlorine dioxide concentration of 1 milligrams per liter. And this is also kind of assuming complete removal of Cn-. Cn/Cn-. At least that's how I'm reading it. So we'll take a look. We have the balanced equation. We can write it as 2.5, or we can just double everything to get rid of the half if you want. So it'd be 5, 2, 1, 5, 2, 2. So 2.5 cyanides plus chlorine dioxide plus half water plus goes to 2.5 of the cyanate ion plus chloride plus H+. So that's our stoichiometric reaction. The ClO2 dose required to oxidize 1 milligram per liter. If we just check for 1 milligram per liter, we could find that. Yeah, and we have 6 milligrams per liter, so that's a. Why is it saying for 1? Anyway, we're gonna just follow their problem here. So I don't know why they are writing 1. This makes no sense to me because this is what they're checking. Anyway, 6 milligrams per liter of Cn-. Do these conversions, we get 6.23 milligrams per liter of chlorine dioxide. Now, the question was, what dose do we need to have in order to have a 1 milligram per liter residual after doing that? So we need to add 1 milligram per liter on top of that. So our dose becomes 7.23. So I wanted to make sure you had that kind of on hand. That would be kind of important to notice the residual concept. What is going on? I didn't ask for any of that. Cool. All right. So part B goes on to say we can take a look. Hang on. What have I done? Go away. All right. Part B says if we take a look at table 10.3, which I showed you in class last time, the oxidation rate of HCN is negligible in comparison to that of Cn-. And if the dose of chlorine dioxide is determined in part A is used, what is the detention time required to oxidize 99% of the cyanide in a CSTR to meet the requirements in part B? Oh, excuse me, I jumped ahead. If the pH remains at 6.5, assume instantaneous equilibrium between HCN and CN minus. Okay, so this is going to bring in equilibrium chemistry into a mass balance, and we have a few things to solve. So I'm going to make a couple of notes here. First of all, we have an equilibrium constant for CN and HCN. This was we can find this, I think, in table 10.3. This is 10 to the negative 9.321. And of course, that's going to be equal to H plus times CN minus over HCN. Another thing we can do is define the fraction that is in the form of CN minus. If you may have seen this before, we sometimes call them alpha fractions. I didn't really go into much depth in this, but we did look at how to solve these problems with the equilibrium, and so this should make some sense. This is just a way to formalize the portion. So we could say that the portion that is CN minus is simply CN minus divided by the total CN. So I'm just going to write that as CN total, where CN total is going to be simply equal to CN minus plus HCN. Okay, so we have that. We can work with that accordingly. The other thing we have from that table is the rate constant for CN minus reacting with our chlorine dioxide. This was from table 10.2. That is 8 times 10 to the third. So 8,000 per mole per second. It's a second order rate constant between our chlorine dioxide and our the cyanide. Okay. So we can calculate a couple things before we get too much further ahead. We can go ahead and calculate our total CN. This is going to be the 0.006 grams per liter, the 6 milligrams per liter, that was given as we were given that we have 6 milligrams per liter expressed as CN minus. So we're going to calculate this in the form of CN minus, simply multiply this by 1 mole per 26 grams of CN minus. The molecular weight of carbon is 14, nitrogen is 14, carbon is 12. That gives us 26. So this should come out to be 0.23 millimoles of cyanide. Well, of total expressed as cyanide. We'll just leave that as moles per liter of cyanide. We can also say that's equal to our CN minus plus HCN. Okay. From here, I want to pause and take a look at what the question is asking and how to formulate a solution for the thing that's being asked. Then we're going to come back to these pieces that we've just discussed and put them together into a solution. So ultimately, we need a mass balance. And we need a mass balance on the CSTR. It's going to be a simple system, well mixed. We have some volume here, some flow rate, some amount of CN total coming in, and some amount of CN total going out. We also have some amount of chlorine dioxide being dosed in here. Now, if you recall what's going on in a CSTR, we have chlorine dioxide being, and everything else being well mixed instantaneously. It's an ideal reactor. So whatever our residual is that's coming out of the system when we're done with the reaction is the same thing as what's in there. So the concentration of our CN total inside that reactor and the concentration of our chlorine dioxide have to be the final concentrations. So we know that what's in the reactor is, if, according to the problem, the 99% removal, we need the concentration in there to be 1% of what came in from the influent. Likewise, we need the chlorine dioxide to be pretty close to that residual that we were targeting, that 1 milligram per liter. Now, there's a slight caveat here. We are only oxidizing 99% of the cyanide, so we actually will have a slightly higher residual than the 1 milligram per liter because we dosed it to remove everything, so we're actually going to bump it up by like 1%. But we'll handle that in a moment. Okay, the mass balance should be some function then where we have a effectively constant concentration of our chlorine dioxide. So this will look a lot like a first order decay where we have a steady state system and we have something going in, Q, and I'm going to do this on Cn. And I'm just going to put that in parentheses. That's total. Actually, for the moment, I'm just going to call it C. All right. We'll say C equals Cn total. So if we set it up that way, this will look very familiar. Minus QC, so QC not coming in, minus QC leaving, plus our reaction term, which will be a decay reaction in that volume. We will have the rate constant described. We will have our concentration and our ClO2, which will be constant and very close to 1, so it's almost as if it is just not a factor. Okay, now, with all of that, actually, if that's in moles per liter, no, that's fine. With all of that, we can solve this for C like we normally would. Well, actually solve it for tau. We need the residence time, right? That's what we're asked for. So we can rearrange this for tau, but we have to recognize something. The reaction that's occurring is only reacting on part of the C. It's only reacting on the Cn minus. So that's where our equilibrium equation stuff will come in and apply to this particular C right here, because what I've written is not actually correct, right? The reaction is not actually acting on C, so we need to revise this. I'm going to put that as a C star for a moment and just say C star is Cn minus. Okay? So we need to handle that a little differently, but it would be very convenient if we could put it in terms of C, the total cyanide. So I'll just simplify this a little bit and pretend like we're doing it normally for a moment. So we would say, if we divide everything by Q, we would get C naught minus C minus tau K. This would normally be C, but I'm going to star it, and another constant, ClO2. Okay, from here, if this was typical situations, we could divide everything by C, and we would get a term where we have C naught over C, or C over C naught, and then simplify in accordance of tau. However, we can't do that yet because the C star is not actually C. So what can we do? Well, maybe we can get C star, the Cn minus, in terms of a function of C, which is the total. right? So then let's think back on our alpha fraction here. We can describe Cn minus as equal to the C total times, I'm just going to call this the alpha fraction Cn minus. The portion that is Cn times Cn total. So what is this alpha fraction? Well, this is going to come from our combination of these two equations, right? Those two will give us an alpha fraction. Alpha Cn minus. We can describe, let's see, do I have it? Might have a simplified form of it. Well, let's just derive it real quick to make sure it's clear. We can get this from saying Cn minus divided by Cn minus plus HCN. Divide the top and the bottom by Cn minus will give us 1 over 1 plus HCN over Cn minus. And now we can relate this to our Ka equation. If we divide our Ka equation, if we divide both sides by H plus, then we have Ka over H plus is equal to Cn minus over HCN. We flip that, that'll be HCN over Cn minus. So this would be the same as saying 1 over 1 plus the H plus over the Ka. All right, so now we have an alpha fraction and that we can calculate at our pH of 6.5. This becomes 5. No, that's part C, sorry. What do I have? Did I solve it? Can anyone do that for me real quick? 1 over, see if you can do it faster than I can. .00186. You can feel free to double check me on that. Funny thing is, I just took my closest Excel sheet and I also have it sitting there solved already. Actually, I have it in my Excel sheet as a given, probably from the... Tell you, the solutions to this book are always a little screwy. They're showing that the alpha would be 1.95. And I just calculated this as 10 to the minus 6.5, 21. Okay, so that's just me, my bad. There we go, okay. Good. All right, we'll come back to that in a moment. Glad that's just me that's wrong. Less scary that way. Okay, so with that, we can take our alpha fraction, put that in for this C star, and substitute it accordingly. So Cn minus then would be this alpha times C is what I'll say. That means C star is equal to alpha C. That means we can rewrite this portion as 0 equals C naught minus C minus tau K C times alpha times our ClO2. Okay, from there, we can divide everything by C and then solve for tau. I'm going to give us, I'm going to say next slide. Already enough of a mess. Okay, so at this point, we can divide everything by C. That was C naught over C minus 1, just double check, minus tau K alpha ClO2. Okay, from here we solve for tau. Go ahead and add it to both sides. Tau alpha chlorine dioxide equals C naught over C minus 1. And then we can solve for tau. Now, we know that C over C naught in this particular scenario is 0.001. That means that C naught over C is 100. So this is really 99 divided by the alpha times our chlorine dioxide. Now, the last piece of this is we need to figure out our chlorine dioxide. And let's see. I think actually I'm second guessing myself right now or the book. I'm not sure which. The rate constant here, I'm not sure if this was calculated with milligrams per liter of chlorine dioxide or if this is moles per liter. I think that's probably milligrams per liter, and then with moles per liter of cyanide. That's what I'm guessing, because then the units will sort out. Does anybody have the book handy? Grab up table 10.3, see if you see anything on that, if you want to. All right, so when we solve this from here, well, we need the chlorine dioxide dose, right? So what is ClO2? We already described that the dose was provided in part A as 7.23 milligrams per liter to leave a residual. You see anything? What's that? Yeah, it's the overall rate constant, like the units are per molar per second, but the per molar, is that coming from the reaction with the chlorine dioxide or the cyanide? That's my question. Okay, so maybe we do need to convert the chlorine dioxide into molar units. Probably. Okay, I don't think I did that in my solutions last time, or yeah, we can convert it. I don't think hang on. Let me just see what the book solutions have. Oh, never mind. Okay, so the calculations I have, I just didn't show that. We do that, yeah. Bless you. All right. Okay, so we have the 7.23 milligrams per liter. That was from part A to give us a residual of 1, but we're actually only going to use 99% of what's consumed. So if we take this minus the 1 residual, that normally is 6.23 milligrams per liter consumed, but we can take that and multiply it by 0.99 for we're not actually converting all of the cyanide. We're only converting 99% of it. So we're not using as much chlorine dioxide. So that gives us a new residual. Should actually be 1.06 milligrams per liter. Then we're going to take that and convert that into our moles per liter units. So we're going to take the 1.06 and we can take that by 1 mole ClO2 per 67.5, or I'll just go ahead and put it into milligrams ClO2, which gives us 1.57 times 10 to the minus fifth moles per liter of ClO2. Okay. All right. So with that, we can finally calculate our tau, putting that in here. All the pieces should come together, and we would get a tau of, actually didn't put it in seconds, but it would be 3.17 hours. Or of course you could convert that into some other unit. Okay, so that was pretty complex, right? A lot of moving pieces there. Does that make sense? Kind of a lot going on, but okay. So I might need to make more room for part C and D, but C says if the pH was raised to 8, what detention time would be required if we use everything else the same. Fortunately, that's going to just simply be a change in our alpha fraction, right? A new alpha fraction. Here, this time it's going to be 5.82. Yeah. Oh, thank you. You're right. Yeah, I looked at the wrong spot. This is the problem when I'm not very organized with the way I'm writing my notes. This is B. Okay, so we have a new alpha fraction. We leave everything else the same, and we put that in, and now we get the tau equal to, let's see. The tau at pH 8, I have as 6.17 minutes. Which is, again, probably in my notes I just have things written funny. So I'm gonna revise and say this is order-wise, that makes sense. What I wrote last time does not make sense. So I think I just made a mistake writing it. So D then asks the same conditions in parts B and C, what happens if we take a plug flow reactor, and that requires some Excel. We'll take a quick look at that, but that would end up giving us the 6.17 minutes. Now, a quick aside, if we take a look at that alpha fraction 5.82, we compare that to what we had in the previous one, which was 0.195 times 10 to the minus 2. At pH 6.5, we have much smaller fraction of Cn minus, which makes sense. We get more protonation at a lower pH. So when we bump up the pH, it's expected that we take a shorter amount of time. We certainly see that going from 112 hours down to 3 and a bit, 3 and a quarter almost. Now, for a plug flow reactor, the big difference is our chlorine dioxide, the initial reaction, we're reacting with a much stronger dose of chlorine dioxide. At the very first minute, we have a minute worth of reaction where we are almost at the 7 milligram per liter dose. So that, in terms of the amount of change that we're going to cause, we have a higher concentration of our contaminant and a higher concentration of our oxidant. So our change is occurring faster. So it's much more efficient compared to mixing it all together. So that's what's going on there, but we need to do some Excel calculations for that or an integration. So I went ahead with the Excel approach. I have ClO2 and a total Cn minus concentration. We have the alpha fraction that we calculated and the new one here. We have our rate constant and the 2 different pHs. Now, if we set this up to calculate the change in chlorine dioxide with every step, that'll be a change according to what we had minus the reaction that occurred. And we can define that reaction, that will be proportional. We'll lose 1 mole of chlorine dioxide per mole we react with. Okay, that'll be proportional in that way. That was the 2.5 moles actually. That's where the 2.5 came from. Divided by 2.5. So on the total cyanide, we can set that up per time step in accordance with the reaction with our chlorine dioxide. So essentially the later problems and 1014, probably just taking this system and being a little bit more complicated with them. All right, so if we do that, we can set this up at the 2 different pHs, and we can also track the final over the initial concentration. And the problem is asking us to find how long does it take until we get to the point, till C over C naught is 0.01. So we can simply just walk this down until we find the spots where we have C over C naught crosses from higher than 0.01 to lower than 0.01. Right there. And call that 4,440 seconds. Or I know this is 330 seconds, sorry. On the flip side, on the lower pH, we have to continue all the way down until we find it right here. Okay. Yeah. Yeah. That I was just kind of realizing that as you said that. So what I should have done here is given us the detention time for PFR at 6.5 and at 8, right? Yeah. And here, where do I have that? 15.7. This is why when you do a homework or an exam problem, it really helps if you highlight it. So clearly I didn't do that. I highlighted some of them, but not all of them last time. Mm-hmm. 3.8 to 4 range. 3.77, 3.9. I mean, that seems, let's see, so, okay. That's believable based on the problem. I'm not confident that I did that correct in the moment right now. So I'll go back and look at that, but I'd rather move on to other problems because I think I just probably made a mistake there if multiples of you got this. I will check that when I grade the homework and figure that out. Okay. So, but the only thing would be to change your alpha fraction and apply it accordingly. Like that would be the only thing that would be required because we set up everything else. So if that is the situation, then my apologies. Okay, is that fine? Good on that? All right, so 10.7, this is the one that was similar to, or most similar to example 10.14. So that's part of why I brought that up. So we have a pharmaceutical diclofenac can be oxidized by either direct reaction with ozone or by reaction with hydroxyl radicals as indicated by the following reactions. We have ozone with diclofenac that makes products with some rate constant 10 to the 6 per mole per second. Then we have hydroxyl radicals reacting with 7.5 times 10 to the 9th moles per second. And the problem asks, in water that contains no carbonate alkalinity, so we don't have any bicarbonate issues scavenging our hydroxyl radicals, compare the rates of degradation of 10 to the minus 8th moles per liter of diclofenac under the following conditions. 1 is pH 6 with 20 micromoles of ozone dose. 2 would be pH 8 with 20 micromoles ozone. And 3 would be pH 8 with 2 micromoles of ozone dose. So what we want to do is, first of all, set up kind of the basics and the rate equations. So we can take a look at these rates. We could look at dC/dt for ozone. This should be, and let me go ahead and write up. I have K1 through 3. If we call this K1, this K2, we might also need a couple other equations. We've taken a look at before ozone plus OH minus is giving us HO2 minus and O2. That would be K3, and a K4 would be ozone plus this HO2 minus, giving us hydroxyl radicals. Okay, I'm not actually sure that we need that, but if we want to be thorough, we could use that. Actually, no, we probably need that. Anyway, we'll talk about that in a moment. I'll go ahead and write these down. These are from that prior example, 10.14. All right, so those would be relevant to ozonation and hydroxyl radicals. Now, actually, I think there is a reason why the problem's not mentioning those. At any rate, change in ozone, then we could take a look as K1 times our concentration of ozone times the concentration of diclofenac. I'm going to abbreviate that to DFC. And then we could have potentially these reactions down here consuming ozone. So this would be K3 times our ozone times our hydroxide, and K4 with the concentration of ozone and the concentration of this HO2 minus. Okay, with all of that, we can find a rate of change of the ozone. Next, we could take a look at the rate of change for our diclofenac, DFC. This would be changing as a function of the reactions with ozone. With diclofenac and the hydroxyl radicals. And we could look at our change in hydroxyl radicals as a function of time according to these equations. HO2. And finally, this other intermediate, HO2 minus, with time according to K3 to generate it. Oops, that's OH minus. All right. So we have all those pieces that we can write out and then consider the three different cases. That's essentially what we are aiming to do here. One thing we might notice, it looks like our hydroxyl radicals react a lot faster than the ozone. That's a 10 to the 9th compared to 10 to the 6th reaction rate constant. However, if we stop and take a look and put in the numbers, we'll notice that we don't end up getting much of any hydroxyl radicals. So the rate at which this is reacting, especially compared to the case in 1014, the rate at which it's reacting turns out it's going to be a lot faster with ozone and negligible with hydroxyl radicals. So our ozone concentration stays approximately the same. Our hydroxyl radicals don't really show up much. And that kind of explains the rest of the problem in terms of part A and B. The effect in part B is only important if hydroxyl radicals are important. Turns out that was important in example 1014, and this is a contrasting problem where it's not so important. Now, to get there, we still need to put in some numbers, and here's where it might be good to use Excel, but really what you're going to do is set up in case 1, we have pH 6, and let's go ahead and say pH is 6, and the ozone is 20 micromolar, and so on, and we would calculate the rate expression, the rate for each step. So we could say then the initial rate for case 1 equals some value. Right? We can calculate that rate for change in ozone. We could calculate that rate for the change in diclofenac, which is the key one. So to address whether or not, let me see if I have more space here. Yeah. So to address whether or not our ozone is really that important, we could check to see how quickly our ozone changes. what is the rate? How much is it changing per time at the very start of our problem? So we can check the initial conditions, the initial rates for each of these cases, and that's where it might be useful to do in Excel. So let me write this up a little more clearly, and maybe we'll get to putting rates. So let's say rate for the diclofenac initial. And we can do that for each one. We could also potentially plot these just like we were doing a moment ago, or example 10.4 did, and it should come out, we should be able to derive a plot like this, although, of course, I was having difficulty with 10.14, so I think I need to revisit some of the assumptions I was making, spend some more time on that. But we should be able to get a plot that looks something like this if you were to use Excel, where this would be our starting condition, 10 to the minus 8 moles per liter. This would be our 2 micromolar ozone case. We would have then a couple others that are a little more like this. So 2 of the cases are pretty close. That's occurring because our change in pH didn't really matter too much. Ozone is reactive enough with diclofenac that it was dominating. So despite encouraging more hydroxyl radicals, the change in pH didn't actually matter very much because ozone was already destroying the stuff fast enough. So I will jump ahead a little bit, and you can see that some of the other part of the problem that we're ignoring. Ozone is dominant. So hydroxyl generation didn't matter much with a pH or alkalinity, the bicarbonate. Okay, so the moral of the story is the amount of ozone made a big difference. The pH, which indicates the hydroxyl radicals, did not. For the sake of time, I'm not going to calculate these. I don't have them on hand, but I will, of course, get those for the solutions. And I'll aim to add these here for you when I post these. Okay. So I will add a little bit more there, but I'd like to cover the rest of the homework. Any big questions here, aside from getting those exact numbers? Okay. Does that make some sense, process-wise? Okay. So 10.9, another complicated problem. This one really calls for Excel. So when HOCl is added to water, it can enter a number of competitive reactions, ultimately determining the concentration and mix of trihalomethanes or other disinfection byproducts. So consider the following elementary reactions. We have ammonia with hypochlorous acid giving us monochloramine. We have monochloramine with hypochlorous acid giving us dichloramine, and bromide with hypochlorous to give us hyperbromous acid. We've got rate constants. We're going to assume that the reaction rate of ammonia with HOCl as well as the reaction rates with ammonia and monochloramine and bromide with OCl minus. So with OCl minus are all negligible, so we don't have to worry about the equilibrium on that one compared to the other reactions. We have a solution that's well buffered, so it stays at pH 8, and it contains 0.5 milligram per liter of total ammonia nitrogen, 0.5 milligram per liter of bromide, and if we dose it with 4 milligrams per liter of chlorine, estimate the times at which A, half of the total ammonium, and B, half of the total bromide have reacted in a well-mixed batch system. And make sure to state and check any assumptions. So this is actually going to be quite similar to, to this problem where we set up a kind of a sequence where we could follow things, follow the progression of different pieces along. However, we're going to need to do it for more, and I also need to revise this spreadsheet a little bit. Where is my cursor? Why is my cursor not showing up? That's annoying. There we go. Okay, so I'm actually revising this, but I wanted to show you some of the process. So we'll get some time step to use. The key here is to go back to what we were doing with problem 3, where we had a portion of our reaction was occurring, because a portion in that problem was Cn minus, but there was a total Cn minus, or total Cn. In this case, a portion of our ammonia will react, but there is a total ammonia in the system, so it's going to make more sense to calculate the actual amount of ammonia using an alpha fraction, and do our reaction with the alpha fraction like we did in problem 10.3, and set it up accordingly. So I'm in the process of rebuilding that to get it appropriately. What it should look like, if you were to do it and plot all these, is it should look like these, where we have the change in each species or the growth in each species based on all of that. We can get the rates of each component according to each of these reactions, and the total rate of chlorine change as the reaction with ammonia plus bromide and the chloramine. So for each rate, we can get a rate equation, the constant times the two concentrations involved, and so on, just like we had been doing before, and working it from there. Do that for the total nitrogen and the total chlorine. And also do a straightforward calculation. Bromide's not in any, we don't need to worry about HBr. Okay, so that would be the setup, getting it all put in. And let's see, do I have... Okay, we don't have much more time left, so I'm going to, let's see, what can I give you? Actually, let's see, do I have them? I don't even think I have the answers on hand, so I will, like I said, I'm going to be quite lenient on that. Apologies again, being overly ambitious here. But I do want to talk about the last couple of problems. I think I gave these both to you, right? So let's take a quick look. These are more discussion. So excuse me, not A, 10.10. Why do we typically characterize a disinfection process by the amount of disinfectant remaining in the water after some period, that residual, after the disinfection dose has been applied? Well, as we saw in the cyanide problem, when we have some reaction happening, the rate of that reaction will be determined in a CSTR by the mixed concentration, the one that has already been going through that reaction. When we reach a steady state, we have one concentration, right? That is what's in that CSTR. It's already been diluted since dosing it with all the other water. So in that case, it's extremely important. In the case of a plug flow reactor, it works a lot better, but it's going to be safer to apply it and assume that some of that chlorine went away really quickly, or the ozone or whatever. So some of that will be instantaneous demand, some of it will be demand over the course of the plug flow reactor. The safest way to design it then would be to treat it as if it's reacting with the lowest amount of concentration that we know is in there for the entire time. It'll get better treatment than that, but that's the safe approach. So 1036 describes the regulation for disinfection byproducts, specify maximum contaminant levels for contaminants analyzed at the outlet from a treatment plant, various points in the distribution system, to assess whether or not the utility is meeting the regulation. In contrast, lead and copper are treated differently at household levels, and that's difficult and not always very accurate. So the question is, why does the EPA insist on that? Well, the Flint water crisis is a good example. Lead and copper could be in our pipes and in our distribution system, and it's really important to make sure that our entire distribution system is operating in such a way that's not corroding that, adding that to the water. We would not have lead coming out of our treatment plant, I should hope, but it's possible that it could come out of the lead in our pipes. Okay. Any other questions? We good? Enough? As long as I'm generous on the grading? Okay. All right. Well, I'll be in touch with final exam plans. Yeah.
Double checking, the final is just on this newer material.
Correct. Not cumulative. All right. Well, good luck on your other finals and on this one, and see you next week maybe.